everybody. I'm Kateryna Lemishko. Yes, and today we'll talk about our machine learning estimator for the appearance of electron fragmentation fragmentation patterns. So, chemistry sets that are typically used in plasma multiplasma modeling, they contain a large number of species that are involved in a large number of collisions, reactions, and the typical challenge that the plasma modeling community faces is related to the limited availability of the input data. That's where for plasma models like rate coefficients and transections, and ideally these missing data should be either obtained experimentally or calculated from first principles, but these approaches are often time consuming, they're difficult and not always feasible, and an alternative way of getting reasonably accurate estimations of this data and quite fast is by using machine learning approaches, but one should keep in mind that the accuracy of machine learning approaches, it depends, strictly depends on the quality and the amount of input data. So machine learning has been previously extensively used in diverse fields of science, and particularly in the fields of computational chemistry and plasma physics. So in the field of computational chemistry, machine learning has been used to predict reaction yields, molecular structure, functional charges, physiochemical properties of substances such as toxicity, bioactivity, solubility, melting points, hydration energies, and etc., etc. And in plasma modeling, machine learning has been used for prediction of total electron ionization intersections, and apart from that, these algorithms were used to predict particle properties of plasma grains, the sputtered particle distributions, characteristics of plasma deposited films, the plasma edge data, and so on. So all these machine learning algorithms and these machine learning models that I mentioned, they fall under the category of supervised machine learning models. So how they work? So these supervised machine learning models, they use known data to identify and learn patterns and relationships between a set of descriptive variables and a target variable that the machine learning model intends to predict. So the process of learning these patterns data is called model training or just model fitting. So the trained machine learning model is expected to give reasonable predictions for new and seen data. So yeah, in the context of electron impact ionization fragmentation patterns, so yes, in plasma physics, it's often desirable to know them, and partial ionization intersections, they can be calculated using branching ratio for the production of fragments, which can be obtained from mass spectrometry data. But the problem is that for many compounds, experimental mass spectrometry data is unavailable, and a way to get the reasonable estimations of this data is to develop an algorithm trained on already existing data. So this is what we've done at Quantemol. So for the task of prediction of ionization spectra, we collected more than 6,500 mass spectra for relatively small compounds of molecular mass below 300. And besides that, we collected the SMART representations for all the compounds from the PubChem database. So SMART is a way to encode the structural information of the molecule using a linear string of characters. So this SMART data actually can be used to extract lots of numerical data describing structural properties of the molecules, like, for example, the data describing atomic features like the types of atoms, the atom balances, the number of neighbors that each atom has in the molecule, the types of hybridization of each atom, whether the atom is aromatic or not. And besides that, we can extract features that describe the bonds within the molecule, like bond types, single, double, triple bonds, like plurality of bonds, whether the bond belongs to ring, whether the bonds are conjugated, and things like that. And besides, as inputs for our machine learning model, we can use general feature describing the molecules like molecular mass, the total number of atoms, total number of bonds, also the this information, the moments, possibilities, and so on. And we can use all these input data that we collected for each species to train a machine learning model to find relationships between this input data and a target variable, which is in our case, is the vector of the mass spectral vector. So the problem here, the problem in our machine learning model training is to predict is the multi-output regression, and we should predict the intensity of each peak corresponding to each m over that ratio. So to actually select a machine learning model, we need to come up with evaluation metric for this model. So in this case, we used cosine similarity score. So here the y real I and y predicted I there are the intensities of all peaks at each over that position. So the goal of so here we aim to select a machine learning model that could give the best median cosine similarity on the test, on the test and validation data. So I can just briefly describe that how our model selection process looks like. So we have all our training data set that contains input features and target variable, and we need to pre-process actually this data set so it can be fed to the machine learning model. So typically this involves computation of missing values, the normalization of features, and the normalization of target variable. And also in this case, we needed to pass all the zero intensities. We need to pass all the mass vector vectors, so the length is the same, 300. And so we split this data into two subsets. One is the test subset that is now used for the model training, and it doesn't participate in the model selection. And the rest of the data we use for model training. So we split this subset of data into training set and validation set, and we train the model, and we perform this procedure several times. So each time our model sees a slightly different subset of data. And we calculate our evaluation metric, and we choose the model that gives the average, the best average evaluation, the best average metrics across these different subsets. So this is the procedure of, this is the procedure of selecting and optimizing each machine learning model. So actually, we follow this procedure and we try different machine learning algorithms, and I can just talk about the 3 best performing machine learning algorithms that gave the best median cosine similarity in our problem. So for example, our best model was random forest. So the random forest model is based on decision tree algorithm. The decision tree algorithm is just a simple algorithm that learns simple rules based on the values of input features. So this way it can predict the target variable. So it splits recursively the feature space and target variable space into different subspaces towards the minimization of the variance in target variable. So random forest, it just typically it builds a large amount of independent decision trees that are trained on random subsets of data and random subsets of features. And the prediction of random forest is just an average prediction over all these decision trees. And our second best algorithm was it's quite a very popular algorithm in machine learning community. So it's an XGBoost, extreme gradient boosting algorithm. So if we talk about gradient boosting trees, this algorithm just fits one single decision tree here on the data, and it creates sequential trees they aim to correct the prediction of this first tree. So they're trained on errors of all the previous trees. So the prediction of this algorithm is just the initial prediction of the one decision tree plus the predicted corrections to this prediction. And our third best performing model was multilayer perceptron, and this is just a simple neural network architecture. So this is just a simple feed-forward neural network, fully connected nodes, and should contain at least 3 layers: an input layer and 1 or more hidden layers, output layer. So the hidden layer receives the signals from all the nodes from the previous layer, and it calculates the weight count of these signals and adds some bias. And then the output from the node is subjected to an activation function that introduces some nonlinearity to the signal. And in the final layer, the output layer, the prediction is made. So again, the weighted sum of signals is calculated, and also in this output layer, which should apply some activation function to like have a desired output of our network. So in our case, the output layer contained 300 nodes. So we predicted independently all the intensities corresponding to all the OM over that value, sorry. And so the fit in neural networks, fit in neural network to data means finding the best set of these weights and biases. So the best fit actually provides the best the minimum of loss function that we choose, which is usually is the mean squared error, whatever. So sorry for this detail. So as you can see, all these models, they provide quite different perspectives. So they treat the fit data slightly different. So usually in machine learning, you can achieve better performance and better predictions actually by combining different machine learning algorithms. So in this case, we combined these three best performing models. And again, we created a single voting regressor in which the prediction of target variables made by summing weighted predictions from different models. And again, we optimized these weights in this process of cross-validation. So we trained the voting regressor on different subsets of data, and we calculated the average score. And this way we selected the weights. Sorry. Okay, so now, yeah, I will show you some results. So these are the distributions of percent similarities for each of these models and for the voting regressor too. So yes, so on test data, so test data has never been seen by the model. It was trained only using this validation and training subsets. So actually, on test data, our best performing model was XGBoost regressor with a median of percent similarity of 0.81. Here, this mean estimator just it's just the average mass spectrum across the training set, which is predicted for all the test cases. So yeah, so you can see that voting regressor was performed significantly better than our best individual machine learning algorithm, which is XGBoost. And so in the case of our final voting regressor, 70% of compounds in the test set, percent similarity was higher than 80%. And I'm just to give an idea how different values of percent similarity look like. You can show you these examples. I can show you this example. Sorry. So in the case, for example, CH3F molecule, the percent similarity between the predicted and experimental mass spectra is almost perfect. So like all the ratios of peak intensities are well conserved and everything is great. For the value of percent similarity of 0.85, it still looks quite decent. And so when the percent similarity is lower, around 0.7 or even 0.5, it's not that great already. So we have the fragmentation, the fractions of the fragments that we can infer from this would be erroneous. But okay, so our mass spectra estimator is available as a web application on PGP and also is available in the desktop application. So the estimator provides a mass spectrum, estimate for mass spectrum, and also the fractions of all the fragments. And we can keep in mind that this branching ratio that we can extract from these data, they correspond to reference energy. So in the case of NIST, it's around 70 electron volts. So to obtain branching ratio, energy-dependent branching ratio needs the appearance energies too. So for this, we'll need to use the quantum chemistry methods. So, but yeah, we'll need the reference energy branching ratio to calculate the partial ionization cross-section. So yeah, so that's it. These are the conclusions. And thank you for your attention.